Whenever you encounter complex mathematical entities, one of the main means of understanding them is invariants. Previously in the RH Saga, we looked at operations on L functions. That could be a unary operation where you give an L function as input and get an L function as output, or a binary operation where you give two L functions as input and get one L function as output. For example, the symmetric square was a unary operation and the sum, or direct sum, was a binary operation. We also had a machine taking two L functions as input and giving a number as output. We did refer to this too as an operation, but a better word is pairing. Our example was the Selberg inner product. Now, there are many other kinds of machines like these. There is a machine called self-dual, which takes an L function as input and gives a Boolean as output. This machine checks if all the Dirichlet coefficients are real numbers. I mean, they could be like I or some other general complex number, but if they are all real, this machine outputs true, or like yes, the coefficients are all real. And otherwise, false, or like nope. This type of machine is called a property. Another machine type is relation. Here you give two L functions as input and get a Boolean as output. Last time we mentioned a family of L functions. A family is a machine where you have a number as input and get an L function as output. Today we will turn this around and look at machines with an L function as input and a number as output. And these machines are called invariants. The overall picture here is part of a general schema of thought that you can use to organize mathematical knowledge around not just L functions, but any concept. Topological space, polynomial, whatever. But our focus now is on L functions, and today specifically on invariants. One of the most mysterious invariants is the conductor. We've mentioned it. It appears in the functional equation. If you give an L function as input to the conductor, it will always give you a positive integer as a result. Take the Riemann zeta function as input. We call it LP. The conductor here is 1. For the L function of k, from the previous episodes, the conductor is 4. In our example, the elliptic curve L function, the conductor is 14. Now, 14 is 2 times 7. Maybe you recall that the bad primes for this L function were 2 and 7. And this is a general feature of the conductor. Its prime divisors are precisely the bad primes for that L function. The Riemann zeta function has no bad primes. Let's go to the LMFDB, go to elliptic curves over Q, and then browse the elliptic curves by conductor. Let's say from 1 to 99. Here, if I scroll down, we see a list of elliptic curves with equations on the right, no one has the mental endurance to always write out the full equation. So instead, we use labels like 11.A1, 11.A2, and so on. And here 11 is the conductor of this elliptic curve. And the A1, A2, and so on just help us distinguish between different elliptic curves with the same conductor. A short way down this list, we find our good old friend 14.A5 with the equation y squared plus xy plus y equals x cubed minus x. Already in this list, there is an incredible mystery. The conductor of an elliptic curve can be 11. It can be 14, 15, 17, 19, 20, and so on. But it cannot be anything from 1 up to 10, and not 12, not 13, not 16. To avoid repetition in this list, choose under curves per isogeny class, just one, and search again. Now we see the sequence 11, 14, 15, 17, 19, 20, 21, 24, 26, 27, 30, 32, and so on. What is the next number? And which numbers, in general, do appear in this sequence? I have no idea. And I don't think anyone knows. But I do believe that the secret hidden here would be another clue in the search for geometry over F1. Now, if you click on an elliptic curve that you like, say 20.A1, and go to its L function, in the right-hand menu, you will find lots of information. First, the Dirichlet series, sort of the L function itself, then the functional equation, and then a list of invariants, including some of the things that I called properties. For this specific L function, the conductor is 20. We knew that from the label. The degree is 2, and we could see that from the Euler factors further down on the same page. Is it self-dual? Yes, it is. Is it rational? Yes. Arithmetic? Yes. Primitive? Yes. And a nice thing about the LMFDB is that you can click on any of these words and an explanation appears. In my head, the L function goes on this talent show audition in front of 4 judges and just like shows off the cosine waves, the functional equation, perfect symmetry, and the judges go like, oh, it's a yes from me. And then it's a yes from me, darling. And then absolutely yes. And then you have 4 yeses. You're through to the semifinals. And the L function go like, wow, that's insane. And like all the L function family, they come onto the stage and it's like tears of joy and all the people. Yeah, but of course that's not how it actually works. Let's go back to the invariants. I want to focus also on the motivic weight. It's 1, and the analytic rank, which in this case is 0. Just for some variation, let's look at another L function. Go to Dirichlet characters, browse by conductor 1 to 9, click the Conrey label next to 4b, and then go to the L function. This is our example LA, the simple periodic pattern. Here, the degree is 1, the conductor is 4, so the only bad prime is 2. You have 4 yeses. And if you ever wanted it, you actually have the spectrum further down. I want 2 more invariants. You could compute the value of the L function at the symmetry point where the horizontal axis meets the vertical line of symmetry. This value is called the central value. Let's write it as CV. If the L function goes to like a job interview, they may ask for the CV. For this L function, it's L of 1/2, and that is 0.667 and so on. So that number is an invariant of the L function. Another invariant is N5. This one just looks at the sequence of Dirichlet coefficients, in this case 1, 0, minus 1, 0, 1, 0, minus 1, 0, and then it picks out the fifth coefficient and gives that number as output. Before we move on to the invariants most intimately related with the Riemann hypothesis, I just want to emphasize that you can always explore many more examples in the LMFDB. For example, here in the Hall of Fame, you find the Ramanujan delta function and its L function, and you could check there what is the degree, what's the conductor, what's the motivic weight, and so on. For any L function, you can compute a sequence of real numbers, lambda 1, lambda 2, lambda 3, and so on, called the Keiper-Li coefficients of the L function. Pick some L function. I pick the L function of k. If you remember, the L function itself does not have a reflection symmetry in a vertical line. But if we multiplied it by these extra factors, gamma c of s and 4 to the power s over 2, then this function that we call lambda of s does have a perfect symmetry. And just a comment, this completed L function is called capital lambda of s, and the Keiper-Li coefficients are called lowercase lambda 1, lambda 2, and so on. And this lambda lambda is just a complete coincidence, reflecting a general lack of alphabets in the world. Now, let's compute one Keiper-Li coefficient, say lambda 3 of this specific L function. I take lambda of s. This is just an ordinary function with some graph. I take log of that. That's again some function. I multiply by s squared. And I get the 2 here from the 3 minus 1. To this new function, I apply the derivative 3 times. And this function, the third derivative, I evaluate at s equals 1. And this gives me just a number. Finally, this number is a bit big, so I multiply by 1 over 3 factorial. Of course, I'm not doing this in my head. That would be a party trick if there ever was one. I am using Sage, and I get that lambda 3 of this L function is 0.3007. That's rounded to 4 decimals. You don't have to use 3 here, of course. The general definition of the nth Keiper-Li coefficient is lambda n equals 1 over n factorial times the nth derivative of s to the n minus 1 times log of lambda s. That function evaluated at s equals 1. And I think this is mind-blowing. But the Riemann hypothesis for this L function is equivalent to all of these Keiper-Li coefficients being positive numbers. So if you can prove that these numbers are positive, you have proven the Riemann hypothesis. This equivalence holds true for any L function. In the article of Brian Conrey, this idea was described in section 17 called Li's criterion. For this specific L function, the numbers are from Sage, lambda 1, that's 0.1009, lambda 2 is 0.2013, and then it's 0.3007, 0.3988, and 0.4950. They certainly look positive. We could compute more, but of course, you cannot compute them all. In a dream world, some new F1 geometry would provide a structural or theoretical reason for these numbers being positive. The Sage code for computing Keiper-Li coefficients looks like this, and you will find it somewhere near this video. Just 3 comments. These numbers are genuinely hard to compute numerically if you go to higher values of n, and you also want high precision. One really cool project is the Fungrim project led by Fredrik Johansson. And here you can find tables with 50 correct digits for some selected Keiper-Li coefficients of the Riemann zeta function. And this was achieved not with floating point arithmetic in the computer, but interval arithmetic, which guarantees a given precision. Second comment. The reason we could even talk about these higher derivatives is precisely that the L function has analytic continuation. Analytic in this context means exactly that you can take derivatives of any order, and you can do so even at this point s equals 1, which lies at the edge of the critical strip. Third comment. The reason that the positivity of the lambda n is equivalent to the Riemann hypothesis is precisely the functional equation. If you want to dive into the details here, I learned about all of this in the PhD thesis of Andrew Droll that you could also find online from Queen's University in Canada. The URL is too long. Just Google Andrew Droll thesis PDF. Very well. We have introduced a number of different invariants, numbers that you can compute from any L function that give you information about that L function. Let's set up a table with just a few of the most important invariants. I will use our 4 standard examples of L functions, LP, that's Riemann zeta, LA, that's the Dirichlet L function, LK, the Dedekind zeta, and LE from the elliptic curve. The invariants I care about now are the conductor, the degree, the analytic rank, the motivic weight, the central value, n5, and the Keiper-Li coefficient, lambda 3. That's 7 invariants for the dwarf lords in their halls of stone. The conductor for Riemann zeta is 1. The others are 4, 4, and 14. The degrees are 1, 1, 2, and 2. The analytic rank for these L functions, 0, 0, 0, and 0. The motivic weight is 0, 0, 0, and 1. Why is it 1? Well, if you remember the critical lines or the symmetry lines in the functional equation, those lines were at s equals 1/2. But for the elliptic curve, that line was 1/2 step to the right. And this 1/2 step is related to the motivic weight being 1. If you found the Ramanujan delta function in the LMFDB, you have seen that the symmetry line for that L function is all the way up at the number 6, and the motivic weight is 11. The central values are minus 1.4604, 0.6677, we saw that one in the LMFDB, minus 0.9751 and 0.3302. N5, the fifth Dirichlet coefficient, these are 1, 1, 2, and 0. Finally, lambda 3, that's 0.0692, 0.2315, 0.3007, that's the party trick computation, and 0.4348. For the elliptic curve, the analytic rank and the central value are connected to the Birch and Swinnerton-Dyer conjecture. We will come back to all of that next time. Now, I want to erase the elliptic curve data because there is some amazing structure to be found among the other 3. Look at the table. Pause the video if you like. What do you see? The first row, 1, 4, 4. 1 times 4 is 4. This looks like multiplication. Second row, 1, 1, 2. 1 plus 1 is 2. Looks like addition. Let's pause for a moment. Is there a reason to expect a relationship between these 3 columns? Yes, there is. The setting here is that in the world of L functions, the objects here form an addition. LP plus LA is LK. And this addition of L functions is reflected in the invariants. Sometimes as a multiplication of numbers, and sometimes as an addition. For the analytic rank, we have 0, 0, 0. Could be addition, could be multiplication. In fact, if we had other examples with, say, 3 and 5 as analytic rank, then the direct sum would have analytic rank 8. And in general, this is addition. The motivic weight. Again, hard to say. With other examples, if we had 3 and 5 here, the sum would have invariant 5. If we had a 12 and 4, the sum would have invariant 12. In general, this is the max operation, and I will add a question mark here because I believe this is true in general, but I'm not absolutely certain. For the CV, let's see, it's not an addition, although it is quite close. It is a multiplication. For N5, addition, and for lambda 3, this is addition. All of these are general patterns that hold whenever you have a direct sum of 2 L functions. But, as you see, the addition of L functions is reflected into 3 different operations on numbers. That is a problem because it would be enormously helpful for us later if we could analyze all of these invariants within the same theoretical framework. So, now, we will try to make all of them additive. For the conductor, its multiplication here, and I can construct a new invariant called the log conductor, which outputs simply the logarithm of the conductor. This is additive, since log transforms multiplication to addition. The values of the log conductor here are log 1, that's 0, then log 4 and log 4. For the central value, there is a problem in that these can be negative, and we don't want to take log of a negative number. One solution is to take log of the absolute value of the numbers. Call this new invariant log CV with absolute value sign. The numbers we get are 0.3787, minus 0.4039, and minus 0.0252. And if you look carefully at these numbers, they are indeed additive, as they had to be by construction. The motivic weight cannot be saved. There is no function like log transforming max into addition. To summarize, if we drop these two and keep the motivic weight as a weird exception, we now have a beautiful table of invariants that are additive. There are 7 Millennium Problems. You could say 4 from pure mathematics and 3 others. Of these 3, 1 is inspired by computer science, that's P versus NP. 1 inspired a bit more by applied math or fluid mechanics, that's Navier-Stokes. And 1 inspired by physics or quantum field theory, that's Young-Mills. Of the other 4, 1 was solved by Perelman, that's the Poincare conjecture. And the remaining 3, those are the ones we are going to solve in these videos. These 3 immortal problems are all related to this little table of invariants we just constructed. The Riemann hypothesis for any L function, so really the generalized Riemann hypothesis, is equivalent to the positivity of all Keiper-Li coefficients. The Birch and Swinnerton-Dyer conjecture, or BSD, says that for an elliptic curve, simply knowing the analytic rank of the L function allows you to determine whether the solution set to the equation is a finite set or an infinite set. And here we are talking about solutions where x and y are rational numbers. Actually, the BSD conjecture says a lot more than that. It's more precise, but we will get to those details next time. It's a story about the analytic rank and the central value. Last Millennium Problem, the Hodge conjecture. There was actually a recent lecture available online by Maxim Kontsevich, Fields medalist, arguing that maybe the Hodge conjecture is actually false. Who knows? In any case, there is a connection to our invariants that I don't fully understand. So I'll try to explain what I think is true, and hopefully we can work out a more precise understanding later, together, maybe with some help from a Hodge conjecture expert. But okay, here is the idea. Take an L function. It will have Dirichlet coefficients, say 1, 4, 0, minus 7, 500. And a gamma factor, say gamma r of s plus 1 times gamma c of s plus 1/2 times gamma c of s plus 3. And this is really a nonsense example that I'm making up in order to just convey the idea. Here the N2 invariant would be 4, the N3 invariant would be 0, and the N5 invariant would be 500. For a motivic L function, there are in fact two different kinds of weight. You have the motivic weight, denoted W subscript AR because it is also known as the arithmetic weight. The idea is that the arithmetic weight is 2 times the number of 5s in N5. What does that mean? Well, 500, if you factor it, is 2 times 2 times 5 times 5 times 5. How many 5s are there? Well, it's 3, so the motivic weight would be 2 times 3, that's 6. The other kind of weight is called algebraic weight, written W subscript alg. Here, the idea is that W alg is 2 times the max of the gamma c terms. And by gamma c term, I mean these numbers added onto S inside a gamma c factor. So here, these terms are 1/2 and 3. The max is 3, and the algebraic weight is 2 times 3, that's 6. Conjecture. The arithmetic weight equals the algebraic weight for any motivic L function. This conjecture should be equivalent to the Hodge conjecture. And the only reason I put a question mark here is that I don't understand why this is the case. The reason I'm saying it should be true is that if we go back to that article of Farmer, Pitale, Ryan, and Schmidt, where we found all the axioms for L functions, then on page 12, you find the definitions of the two weight invariants, and on page 13, it says, Hodge conjecture, algebraic weight equals arithmetic weight. Inspired by the connections to RH and BSD, it makes sense to establish a general language for talking about all of these additive invariants. And now we are entering somewhat abstract territory, but this will be incredibly helpful later for organizing the concept space around these conjectures. Last time, we talked about the set L of all L functions. This set has an addition. Conjecturally, it also has a product. That would follow from Langland's functoriality. Conjecturally, it also has an inner product or scalar product. This would follow from another conjecture called Selberg orthonormality. Even if we only have the addition, and this is known, not conjectural, we can talk about the dual space of L, as in linear algebra. What's that? Well, this is the space of all additive invariants. Sometimes additive invariants are referred to as functionals. This dual space is denoted L star. A slightly unusual detail compared to other duality settings in mathematics is that the scalars, the numbers that you can multiply with, are different in L and in L star. In L, the scalars are the integers, and in L star, the scalars are the real numbers. But this is not important at all. What's important here is that these two spaces will be the arena for many, many different phenomena we will encounter on this voyage. Every L function is an element of L. What are the elements of L star? Well, every prime can be viewed as an element here by identifying, for example, 5 with the invariant n5. Every prime power is also an element here, but before we can explain exactly how, we sort of first need to talk about something called finite fields. The log conductor, the degree, the analytic rank, all the Keiper-Li coefficients, and many more invariants, all of these are also elements of L star. So, in some sense, they can be viewed as generalized primes. There is so much more to say here and so many questions to ask, but we will come back to this arena again and again, building up an increasingly sophisticated picture of the patterns and interactions here. For now, we have established names for two of the most fundamental spaces in all of math, and we will be exploring them both in great detail. We have touched on three high-level concepts that are central to what we are trying to do in Season 1, but not necessarily something that everyone has learnt about in school. If you know them, they will make it much easier to make sense also of everything else. The first one is lambda rings. And a comment, the lambda in lambda rings is unrelated to the Keiper-Li lambda and also to the completed L function lambda. I brought this book by Donald Yao just to show one place where you could learn about lambda rings. The second concept is finite fields. This yellow book is a solid reference where you will find lots of introductory algebra and number theory, including, towards the end, some theory of finite fields. The third concept is Hilbert spaces. And here I brought one of my favorite math books ever. And I think that is because I got hold of this book at a time when I was an undergrad. I knew next to nothing, but I was very interested in functional analysis. And I found it immensely fascinating that you could, in a single book, start with the axioms for set theory and go all the way up to Hilbert spaces, Banach spaces, and C-star algebras. Also, this entire book series, the SUMS from Springer, it's just brilliant. You could go to the Springer website and look at all of those books. And if you're into math books and you're rich, then just buy them all. But Hilbert spaces. All of the math leading up to Hilbert spaces is explained in this book, including in chapter 5.3, the concept of a dual vector space that we also mentioned today. Okay, one extra book, a bonus book. I love books. This is Topology of Numbers by Alan Hatcher. And this one is freely available online from the author's webpage. The entire book. And it's splendid, unbelievable. All of it really, but from page 195, there is a geometric proof of quadratic reciprocity. And in chapter 8, he talks about quadratic number fields, which will be, for us, one of the main focus points in Season 2. As the very last point for today, you can go to the Clay Institute website and find stuff about the Millennium Problems. Pick a problem, say Riemann, then under Advanced you will find the official problem description. All of those descriptions are very interesting, of course, but for us, most of all, the Riemann hypothesis and also the BSD conjecture, which will be the theme of the next episode.